So this lesson is an introduction to combinatorics. Now you might ask yourself, what is combinatorics? Well, broadly speaking, it's a mathematical study of counting. Now you might think you know how to count, but as you'll see, counting problems show up very frequently in MathOlympiad, and learning the best mathematical techniques for counting a particular problem is invaluable. So let's consider the rule of summing, or the rule of adding. Consider this problem you probably knew how to solve in kindergarten. There are two plates, one with 3 apples and one with 2 pears. You can only take one piece of fruit. How many options do you have? Well, the solution's pretty simple. You can take one of the 3 apples, or you could take one of the 2 pears. So there are 3 plus 2, or 5 different options to take one piece of fruit. This, of course, assumes that all of these pieces of fruit are different. We'll discuss a little later what happens if some of the items you're choosing from are identical. So we've just used an operation called the rule of sum, or the addition principle. Simply stated, it's the very intuitive idea that if we have a number of ways of doing something and b number of ways of doing another thing, and we cannot do both at the same time, then there are a plus b ways to choose one of the actions. Now, obviously, if there's overlap between the two sets, in other words, if we could do one or both at the same time, then we have to be careful about applying the rule of sum. This principle can be extended for many options. So if you have 5 plates with 10 apples on each, there are 10 plus 10 plus 10 plus 10 plus 10. So 50 options, or 50 ways you can pick one apple. Now let's talk about the rule of the product, or the multiplication principle. So we're now going to grow the problem a little bit more complex. Maybe this is something you figured out how to do in 3rd grade. There are 2 plates, one with 3 apples and one with 2 pears. You can take 1 apple and 1 pear. How many options do you have? Well, the solution is not that hard. You can take one of 3 apples, so you have 3 options for the first choice. And then for each of those 3 choices, you have 2 options for selecting the pear. So you have 3 times 2, or 6 different options to take 1 apple and 1 pear. So to solve this problem, we've just used a very simple example of the multiplication principle. Stated most basically, if there are A ways of doing something and B ways of doing another thing, then there are A times B ways of performing both actions. Again, we have to be careful that in doing the first action, we don't impact the second action. So if A and B are uncorrelated, then we have A times B ways of performing both actions. We'll talk later on about what happens if there are interdependencies between the 2 actions. So as with the sum principle, this product principle may be extended to many options. So if I have 5 plates with 10 apples on each, then there are 10 times 10 times 10 times 10 times 10, or 100,000 options to pick 1 apple from each plate. So we pick 5 apples, 1 from each plate, and there are 100,000 ways we could do that. So both the sum rule and the product rule are called the basic counting principles. So on this slide, we'll talk about permutations. In a mathematical sense, a permutation considers all the ways a set of objects can be arranged. So if you want to count all of the ways a set can be arranged, then we're talking about all of the possible arrangements or permutations of that set. And the order of the objects within the set is usually very critical in a permutation. and distinguishes one permutation from another. So now let's talk about a problem that maybe you got to in 5th grade. There are 5 different fruits on a plate: a red apple, a pear, a strawberry, a peach, and a green apple. You have to take all of them one by one. And how many different ways can you do that? In other words, how many different orders of selection are there for picking all 5 fruit? So let's consider the following solution to this problem. The first fruit can be any one of the 5. So we have 5 options for taking the first fruit. After we've made that selection, there are 4 fruits left. So we have 4 ways to choose the second fruit. There are 3 pieces of fruit left, and we have 3 ways to pick the third fruit. Now there are only 2 pieces left, so there are only 2 ways to make the 4th selection. And since there's only 1 piece of fruit left, that decision is kind of made for us. So by the product rule, we have 5 choices for the first choice, 4 choices for the second choice, 3 for the third, 2 for the second, 2 for the fourth, 1 for the fifth. So 5 times 4 times 3 times 2 times 1, which equals 120 ways to order the picking of these 5 fruits. In combinatorics, a permutation is an ordered list of objects from a set. To find a number of permutations of n distinct objects, and we call this P sub n, subscript n, we need, according to the rule of the product, to multiply the following numbers: n times n minus 1 times n minus 2 times, and we continue multiplying until we get to the last object. This product is called the factorial and is denoted by n exclamation point. We do not shout n, it's n factorial, not n. So for any positive integer n, n factorial is equal to 1 times 2 times 3, etc., n minus 1 times n. Or n factorial is the product of all positive integers from 1 to n. Just for completeness, we define 0 factorial equal to 1 because there is 1 permutation of the empty set of objects. So now let's move on to the rule of division. Let's simplify the previous problem. There are 5 different fruits on a plate, the same 5 fruits as before, and you have to take 3 of them one by one. In how many ways can you do that? So again, you have 5 ways to pick the first fruit, 4 ways to pick the second fruit, and 3 ways to pick the third fruit, and then you got to stop. So there's 60 ways to pick 3 fruits out of 5, one by one. There's another way to think about the solution that considers all of the ways to pick the 2 remaining fruits. We get the exact same result as this previous way of doing it. So think about, we have 5 factorial ways to pick the 5 fruits one at a time, but there are 2 times 1 ways to pick then which 2 fruits we're going to give back. So that way we're left with 3 fruits. So you see we have the 5 factorial ways to select all 5, and then the 2 factorial ways to pick which 2 we return, leaving us with 3. So we have 5 factorial divided by 2 factorial, which equals 60, the exact same solution we got when we stopped after picking the third fruit. So the second approach, where we divide the total number of ways by another number of ways, is called, uses the rule of division. So if some options are considered the same, we can divide the total number of options by the number of options we considered the same. So in this case, we had 120 ways to pick the fruit. We only cared about 3 pieces of fruit, so it didn't matter what the last two pieces of fruit were. Those two were going to be considered the same. There were 2 factorial ways to pick those last 2 pieces of fruit, so we divide by 2 factorial. So if we have n objects and want to arrange k of the n in a row, there are n factorial divided by n minus k factorial ways to do that. So in the previous example, we had 5 factorial divided by 5 minus 3 factorial, in other words, 2 factorial ways to do this. This is also called the k permutation of n and is denoted by p superscript n subscript k, or you'll often see it written as p parentheses n comma k. So it's the permutation of n objects and arranging k of them. So let me give one final example of permutations using this rule of division. So let's suppose we wanted to take these 5 pieces of fruit and arrange them in a line. Well, that's just ordering the pieces of fruit, so it's 5 factorial. But what if we wanted to arrange them in a circle and all we cared about was the relative position of the fruits in the circle? So all 5 of these are considered the same because going clockwise, we're always going red apple, pear, strawberry, peach, green apple. See, all 5 of these have the exact same order. The only thing we changed was the starting position of the 5 of the apple. So it could start here, or 1 over, or 2 over, or 3 over, or 4 over. So in this case, the total number of ways to arrange the 5 elements in the circle, if all we care about is their relative position, is 5 factorial divided by 5, which equals 24. And again, that's just using the rule of division. We had 5 arrangements that are considered the same for each option. So we just take 5 factorial and divide it by 5. Now, up until now, we've considered every item in the set different. Even if we had 3 red apples, we assumed each apple was subtly different and we could tell them apart. So now let's talk about what happens if we can't tell elements apart, or permutations with identical elements in the set. So going back to the first example, we have 3 red apples, 1 pear, 1 strawberry, and it asks, in how many ways can you take all of the pieces of fruit one by one if all apples are considered the same? So we already know that there are 5 factorial, or 120 total orders, if all the apples are different. But consider the options when the apples are chosen first, second, and third. So we have apples in the first, second, and third position. Well, there are 3 factorial, or 6 ways to arrange these 3 apples. Okay, so whenever I start off picking 3 red apples, there are 6 possible ways I can do that. But if all the apples are identical, I can't tell these ways apart. So there are 5 other orders that are the same if I pick one group of 3 red apples. We can't distinguish the 6 ways from one another. So we need to divide the total number of permutations by 3 factorial. So we have 5 factorial, and we're dividing it by 3 factorial. 120 divided by 6, or 20. This is just an application of the rule of division. Once we've said these apples are identical, and there are 3 of them, that means for any given arrangement of the fruit, there are 3 factorial identical arrangements. So in that case, we have to divide the total number of permutations, 5 factorial, by the number of identical arrangements, which is 3 factorial. So let's expand this to when we have two different identical elements. So now I have 3 red apples and 2 strawberries, and now I can't tell the apples from one another, and I can't tell the strawberries from one another. So applying the rule of division, I now have 5 factorial arrangements divided by the 3 factorial ways I can arrange the identical apples, and I also need to divide by the 2 factorial ways I can arrange the 2 identical strawberries. So I have 120 divided by 12, or 10 possible distinct arrangements. We can generalize this. If I have a set of n objects, capital N, and there are n sub A, n sub B, and n sub C number of copies of identical objects A, B, and C, then there are n factorial divided by n sub A factorial, n sub B factorial, n sub C factorial permutations in the set. Of course, this could be 4 different kinds of identical objects, 6 different. We just can generalize it to the total number of objects in the set factorial. And because this identical objects are going to limit the number of distinguishable sets, I just find how many of type A are identical, how many of type B, and any other type that are identical, and just take those number of that type that are identical factorial, because I can use the rule of division to eliminate identical elements in the permutation. Next, we'll talk about permutations with limitations or restrictions. So these limit the number of ways we're allowed to arrange the elements, so it's going to reduce the number of permutations. So consider the problem. There are 3 algebra books and 2 geometry books. In how many ways can you put them on a shelf, given that the subject books have to be kept together? So we have to keep the 3 algebra books adjacent to one another and the 2 geometry books adjacent to one another. We can't stick an algebra book between the 2 geometry books. So if there were no restrictions, there would obviously be 5 factorial or 120 ways to arrange the books. But now let's solve this problem. First, we need to decide which subject will go first. Algebra could go first or geometry could go first. So there are 2 factorial ways to arrange the 2 subjects. Then we need to decide the order of the algebra books and the order of the geometry books. There are 3 factorial ways to arrange the 3 algebra books. There are 2 factorial ways to arrange the 2 geometry books. So, using the product principle of counting, the total number of arrangements is 2 factorial for the ways to order algebra and geometry times the 3 factorial ways to arrange the algebra books times the 2 factorial ways to arrange the geometry books. So 2 times 6 times 2 times 24. When additional restrictions are imposed, the situation is transformed from a simple permutation problem to one with restrictions. So there are a lot of ways they could throw restrictions on you in MathOlympiad contests. They might restrict where you're allowed to arrange things, might restrict that certain things have to be next to other things, might restrict that it's a round table instead of a line, say it's a keychain instead of a ring. So you'll just have to use your understanding of permutations and counting principles to figure out how to apply those principles to take into account these restrictions. Oftentimes, we'll need to resort to cases. In other words, instead of solving the whole problem as one, you break it up into 2 or 3 different cases that are easy to solve that allow you to take into account the restrictions. So in this problem page, we talk about some examples of problems with permutations. So we've often been talking about having a limited supply of fruit, but what if we had lots of fruits So our choices from one selection to the next aren't limited. We never run out. So suppose we have 4 large bags with fruit, lots of apples, pears, peaches, and strawberries. So we need to pick 5 fruit one by one. In how many ways can you do it? Okay, so we're never going to run out of any variety in this problem. So let's consider the first fruit. We have 4 options to choose from: apple, pear, strawberry, and peach. For the second fruit, we still have 4 options because I still have lots of whatever fruit left that I picked first. And we have 4 options for the third fruit, 4 options for the fourth fruit, and 4 options for the fifth. So the total number of ways is 4 times 4 times 4 times 4 times 4, which is obviously 4 to the 5th power, or 1,024 ways. Okay. So sometimes permutations are not always about multiplication or division of factorials. You need to keep an eye for the exact wording of the problem and use the rules of sum, product, and division with your best judgment. So as you work more and more of these kinds of combinatorics problems, you'll see how to get good at using these rules. And it's sometimes some complex problem-solving skills, multi-step problems to get to the solution. Now here's a very famous example of a permutation problem that is critical in the field of number theory. And I cannot tell you how many times a year knowing this will be useful in math contests. So please understand this. And if you don't understand it, ask us to go over it in class. Find the number of divisors of the number 60. This can also sometimes be asked, find the number of distinct factors of the number 60. So basically, how many numbers or integers are evenly divisible? Can 60 be evenly divided by with no remainder? And this has to, of course, include 60 and 1 itself. So to solve this, let's write 60 as the product of prime numbers. And we're going to do this because this will avoid double counting. Once I break it into prime factors, I'm never going to have a situation where I had multiple ways of choosing these to multiply one another and come up with the same number. And when you learn more about prime numbers in our number theory lesson, this will become clearer to you. So 60 is equal to 2 times 2 times 3 times 5, better written as 2 squared times 3 to the first times 5 to the first. So any divisor of 60 must be some combination of these prime numbers, right? Let's count all of the combination of prime factors of a divisor. Okay, so we could have factors of 2. We could have 0, 1, or 2 factors of 2. Remember that we have to count 0 in case the factor we're considering is an odd number, or 1 itself, right? So 15, for example, 3 times 5 is a factor of 60 that uses no powers of 2. A divisor may have either 0 or 1 factors of 3, and similarly, it could have 0 or 1 factors of 5. So hopefully you see that now we've turned this into a combinatorics problem. So to figure out how many possible ways I can get to 60, all the different ways I can multiply our factors to get 60, it's like I have 3 plates: a plate with 2s, a plate with 3s, and a plate with 5s. And I can choose none, 1, 2, or basically up to the maximum number of factors available on each plate. So there are 3 options to choose from the plate with 2s, 0, 1, or 2. There are 2 options to choose from the plate of 3s, no 3s or 1, 3. And there are 2 options to choose from from the plate of 5s, 0 or 1, 5. So that's 3 times 2 times 2, or 12 ways. The reason we write it as 2 plus 1, 1 plus 1, and 1 plus 1 is, in general, I can just take the exponent of any given factor and add 1 to it. And that adding 1 to it accounts for the fact that I could choose no factors of that. So 2 squared means I could pick 3 factors, 1 or 2 powers of 2, or skip a factor of 2 altogether. So please take some time to think about this. Maybe pause the video now and write out yourself all the factors of 60, including 1 in 60, and convince yourself that there are 12 of them. This is a very important lesson to understand. So in permutations, the order in a set is critically important. Combinations typically do not care about order. So let's show how we move from our rules for permutations and get to counting combination. So going back to fruit, we have our 5 fruits. What if they asked, in how many ways can you take 3 of them from the plate if order doesn't matter? Well, we knew that there are 5 times 4 times 3, which equals 60 ways to select 3 fruit one by one. But there we cared about the order of selecting the fruits. But now in this problem, order is not important. So for any 3 given fruits you pick, there are 3 factorial, or 6 ways to select them one by one. That means that each way to take 3 fruits was counted 6 times. So as a result, the total number of ways would be, 5 factorial divided by 2 factorial, our original 60 ways here, and then we divide that by the 3 factorial ways we could have picked the 3 fruit. So we get 120 divided by 12, or 10 ways to pick 3 fruits from the plate if order didn't matter. So a combination is a way of choosing elements from a set in which order does not matter. To find the number of combinations of k unordered elements from a set of n distinct objects, denoted by C superscript n subscript k, or C parentheses n comma k, we first find P superscript nk, and then, according to the rule of division, we need to divide by the number of identical ways to arrange the k elements, because we don't care about the order in which they were selected. And we did care about the order in P sub k. So combining everything together, we find that C of nk is equal to n factorial, the total number of permutations of n, divided by k factorial, also divided by n minus k factorial. The most common notation of the number of combinations is the binomial coefficient, written as parentheses n on top and k on the bottom, which reads n choose k. You'll see when we talk about, multiplying the binomial a plus b to the n power, why this is called the binomial coefficient. So believe it or not, I know there was a lot in this lesson, but this was really an introduction to combinatorics. It's an incredibly rich and interesting field in mathematics. I think we covered the vast majority of combinatorics problems you'll experience on contests this year, but there are some more advanced techniques we'll learn about in further lessons. But to summarize today's lesson, let's talk about one example where problems can look similar, but you have to be aware of the specific conditions and how they will change the way they count. There are 4 sets of objects, 4 cups, all different, 4 glasses, all the same, 7 teaspoons, all different, 10 sugar cubes, all identical. And we need to count the number of ways to put A, teaspoons into cups, or B, sugar cubes into cups, or C, teaspoons into glasses, or D, sugar cubes into glasses. Even though the problems look the same, the solutions are significantly different. Let's look at the solutions. For counting the number of ways teaspoons can be put into cups, this may be solved using permutations with identical elements. Every spoon may be put into 4 different cups, so the answer is 4 to the 7th power. B, to put the identical sugar cubes into the different cups. This is an example of the classic ball and urn, sometimes called the star and bar. We're going to see this in our next combinatorics lesson in a few weeks. And believe it or not, it's easily calculated as 13 choose 3. So a combination of 13 objects counted 3 at a time. And you'll learn in that lesson why this is the case. Choice C, how do we count the number of ways to put the teaspoons into glasses? This can be calculated using the rule of sum. And again, we'll learn how to do this in a later lesson. These are also known as Stirling numbers. And the last one, how to put the 10 identical sugar cubes into the 4 identical glasses. If this was a very large number, we'd have to use something called a Young tableau, which is well beyond anything you would experience in a middle school math contest. But if it's a simple enough problem, you can break it down into all the distinct cases. So when you do this kind of brute force, breaking it into all the cases, that technique is called case bashing. Put your head down and write out all the instances, and you could find out the answer is 23. And we'll practice case bashing in a future lesson as well. So today, after this lesson, you'll move on to the exercises. First exercise, prove that taking a combination of R of n objects is always equal to taking n minus R of n objects using the formula we showed in this unit. Obviously, this can also be proven with logic. Since we are choosing R out of n, we are equivalently not choosing n minus R out of n. The second exercise, if n equals 100, find the value of n minus 1 factorial divided by n plus 1 factorial. Third exercise, a yogurt shop has 4 different flavors and 6 different toppings. If a customer picks 1 flavor and 2 different toppings, how many different combinations are possible? 4, how many 3-digit numbers are palindromes? Remember, a palindrome is a number that reads the same forward and backward. 5, in base 7, there are 7 possible digits, 0 through 6. How many possible 4-digit base 7 numbers end in an odd digit? Exercise 6. A Ferris wheel has 8 identical chairs that hold 1 rider each. How many different ways can 8 riders be seated on the ride? If we can only distinguish the relative orientation of the riders while the wheel is spinning. So if you're unfamiliar with it, a Ferris wheel is a circle. 7, how many different 10-letter code words can be made with the letters in Crittenden? In other words, how many distinct arrangements of the 10 letters in Crittenden are there? And 8, how many 4-digit ATM passcodes can be made if the first digit cannot be 0 and all 4 digits cannot be the same? So this is an example of a permutation with a restriction. And finally, the challenge problems. Number 1, how many odd positive integers are factors of 480? So hopefully you could understand how we found how many divisors there were of 60. And now it's a similar technique, but there are restrictions because we only want you to count the odd positive factors. 2, my son Noah is super into Beyblades. There's these fancy circular tops. A circular Beyblade has 5 spots where decorative stickers can be placed around its edge. The bay is otherwise perfectly symmetric. So we can only distinguish a bay by the relative orientation of the 5 stickers arranged in a circle. If you must select 5 unique stickers out of 10 unique choices, how many distinguishable bays can be created? 3, 2 parents are taking 2 children and 4 of their friends to see a movie. They fill out all seats in an 8-seat row. How many arrangements are possible if a parent must sit on each end of an aisle and their 2 children must be seated next to one another? And finally, problem 4. This problem, believe it or not, was taken from the American Invitational Mathematics exam, which is the exam right before qualifying for the high school level MathOlympiad. So it is definitely a challenging problem, but I think some of you will be able to get it, and you should feel really proud of yourselves if you can. A game uses a deck of n different cards, where n is greater than or equal to 6. The number of possible sets of 6 cards that can be drawn from the deck is 6 times the number of possible sets of 3 cards that can be drawn from the deck. So find the value of n. In other words, how many cards n are in the deck so that the number of possible ways I can draw 6 cards from n is 6 times larger than the number of possible ways I can draw 3 cards from n. So that's it for today's lesson. See you in class.